Hello everyone. In the previous lecture we were discussing spin polarization and half metals, and now we are ready for spin injection and spin accumulation. Today we are going to speak about such heterostructure, such bilayer, which consists of ferromagnetic metal, for example cobalt, iron, or nickel, or permalloy, or half metal, any other magnetic metal. And on the right side, there is a normal metal, silver, gold, copper. As I said in the previous lecture, the interface is of very high importance for spintronics. So you need to make sure that there is no oxide layer here, that you have really good conducting layer in between. But for today, we just assume that the interface is perfect here. So our task for this lecture is to understand what means this term, this spin diffusion lens, spin injection, and spin accumulation. So if you have original steady state, then you know that in ferromagnets you will have this balance between spin up and spin down electrons. So there will be more electrons with one polarization, less electrons with another polarization. And in normal metal, the situation will be different. There is no exchange interaction here. Therefore, there will be the same number of spin up and spin down electrons. Now we apply difference in potential, electric potential between these bilayers and generate a current in a way like it's shown here, that electrons start to flow from ferromagnetic metal into normal metal. As you know, if this material has non-zero spin polarization, it means that there is a disbalance between spin up, spin down electrons, and this disbalance is then injected into normal metal. So it means that you simply inject more majority electrons in normal metal, and although it was in equilibrium before, now we will have a different situation, and we will make our normal metal kind of partially magnetic because we will have here more spin up electrons. And this injection of spin is named actually spin injection. Of course, I should tell you that this is the only one mechanism how you can inject spins into normal metal. So there are other also. For example, if you will excite magnetization, instead of applying electric current, you can excite here magnetization precession, so-called spin pumping mechanism. Then you also will inject spin current. Or there is so-called spin-Seebeck effect. So if you create potential in thermal gradient across the interface, you also will create spin polarized current, inject spin polarized current into normal metal. But these two we will discuss later. Today, let us speak about the classical approach when we send current through this interface. So spin injection is clear. What is spin accumulation? In principle, spin accumulation is just an accumulation of your spin polarized electrons here at the interface. I show you here two definitions. So in this definition, we are talking about the spin accumulation. It's an overflow of electron with one spin polarization. But you can define also it already slightly differently, like it's done in the Krishnan book, since spin polarization of electron is associated with magnetic moment, and then you can speak about total magnetization. Then we can describe spin accumulation as a non-equilibrium in magnetization delta M across the ferromagnetic non-magnet interface here. So when you inject spin up electrons, then you will get kind of efficient magnetization. What is spin diffusion lens? Let us switch to the next slide here. So in this picture, you can see that our bilayer structure, ferromagnet normal metal, but the switch is off. So it means that we will get the following band structure. As we discussed, for normal metal, there is no difference between spin up and spin down. This band structure is symmetric, but for magnetic metal, we have exchange interaction which shifts this gap, this band up, and then we have different density of electrons at the Fermi level. If you apply current, if your switch is getting on, then what you will get spin accumulation into the normal metal, and in the band diagram you can show it like that, that now we injected more spin up electrons with respect to spin down, and this difference, if you will summarize magnetic moment from all these electrons, you will get a certain magnetization here at the interface. But what happens after the interface? Because if you keep current on, you can assume that I inject more and more electrons, and at some point, all my normal metal will become a magnetic, because it all will be filled with majority of spin up electrons. But it's not the case, because especially in the case when steady state, when the natural state for normal metal to have the same number of spin up and spin down electrons, you kind of stimulate the spin flip scattering event. And it means that when electrons continue moving from the interface into normal metal, they spin flip scattering event will take place. And it means that after a certain distance away from the interface, your current here, if this metal would be longer, the current would not be any more spin polarized. It would be just a normal current like you usually have in normal metal. And then in some sense, you will get a dynamic equilibrium between the spin accumulation, so injection of your spin polarized current, and spin relaxation associated with spin flip scattering events. And the distance, so you can describe it, the spin accumulation decays exponentially from the interface and is defined by a characteristic spin diffusion length, LSDN. Yeah, so such parameter we'll use in this lecture. Of course, you can have it differently defined with different letter in different sources, but that's how it's done in this book. That's what I'm using. So spin diffusion length is nothing else as a distance, or 1 over E distance of spin polarization, which propagates our spin polarized current in the normal metal from the interface where it is injected. Let us try to define it. So here is a sketch what is actually going on with our electrons. This is our interface for magnetic layer, normal metal layer. And when electron moves, it of course is scattered on phonons, on impurities and so on. And then what we need to define few parameters. And first one is lambda up, which is nothing else as a mean free path of electron for spin up polarization. So do not mix up these scattering events. These are not spin flip scattering. Yeah, so after this point and in this point, spin electron keeps its spin polarization like it was. So this is just standard mean free path of electrons, which we discussed at the very beginning, with the only difference that now we introduce 2 of them for spin up electrons and for spin down electrons. So this is different. And also the relaxation time we need now to separate for spin up and spin down electrons. Okay, then so now we will use spin up, but again, it's just to choose one of the types of electron. There is no more in-depth physics behind. But coming back to the question of spin diffusion length, as you can see in this figure, our electron will go through such a complex trajectory, and then at some point, there will be spin flip event. And the distance which electron propagates before we change its spin is named a spin diffusion length, this parameter. So we need to choose some coordinate and usually along which electric current is oriented, and we define then this projection here as spin diffusion length. How to calculate it? First, what we need to do, we need to introduce this parameter n, which is number of collisions of electron before it change its spin. So in this case, it means 1, 2, 3, 4, 5, 6, 7, 8. So n is equal 8. After 8 scattering events, the spin changed its polarization. Yeah. Of course, since the time which electrons moves between these two scattering events, average time, tau up in this case will be much smaller than tau spin flip, spin dependent scattering event. So the relaxation time of spin dependent scattering event is defined here with this tau up and down, and obviously it's much larger than tau up or tau down, so at least 8 times, yeah, like we just have calculated now. Now the next question, so how we can define the spin diffusion length? For this, what we can do, we can use, first of all, 3-dimensional random walk. So there is such approach when you speak about random walk, and then the distance which your electron propagates after n scattering events can be found as lambda up. So this average mean free path multiplied with square root of n, square root of scattering events. But since we need to speak about 3-dimensional structures, you add here this 3. Therefore, so this is the spin diffusion length in terms of mean free path of electron. And on another hand side, if you will analyze what distance electron propagates, then you simply multiply the scattering number of events. This is length of this trajectory, and this you can simply define as n times a mean free path lambda up. Or moreover, you can rewrite it via the multiplication of Fermi velocity of electrons. So this is speed with which electron was moving times this tau spin flip. So you need to measure as long as electron has reached this point when it changed its spin polarization. And of course, we ignore here the fact that after each scattering event, electron is getting deaccelerated and then accelerates again. So let this model, simple model works good. And then having this value, what you can do, you can simply make, so this is your L spin diffusion. So it's here, and you just replace this n from this formula. And then what you will get such a formula for spin diffusion length, which tells us that it is proportional to square root of Fermi velocity and to square root of the spin flip relaxation time and the square root of spin electron mean free path. So this is the formula for the spin diffusion length. Okay, how large is spin diffusion length? Let us estimate it. First, what we need to do, we just use the value for Fermi velocity, the same one which we used in past, so 10 to the power of 6, 2 orders of magnitude smaller than the speed of light. Mean free path, we take 5 nanometers. The spin flip relaxation time, you remember that normal relaxation time for electron associated with this lambda, we were using 10 to the power minus 14. And now it's 10 to the power minus 11, which tells you immediately the knowledge that we expect to have spin flip scattering event every 1,000 scattering. Yeah, so 1,000 times less often than normal scattering. And if you plug these values into the formula which we obtained, then to this formula, then you will get that you should expect spin diffusion length to be of order of 100 nanometer. And this value agrees very well with experiment. For example, for gold, for silver, or for copper, which are considered to be a good spin conductor. So it means that if you need to send spin polarized current over a long distance, then you use usually copper or silver. And in these materials, the measured values are up to around 500 nanometers. Yeah. Nevertheless, if you will induce, will dope your material with manganese or platinum, or principally any other impurities, especially with large spin orbit interaction, then you can reduce this spin diffusion length significantly. 10 or 30 nanometers. Or if you will use simply heavy metal with large spin orbit interaction like platinum or palladium, then you also will get spin diffusion length of order of 10 nanometers. Final question I would like to ask to address here is how many spin polarized electrons do we have at the interface when we perform this, when we do spin injection and obtain spin accumulation. As we discussed, this X is a coordinate which goes normal to the interface, and then you inject it into normal metal n equals 0. So this is n0, it's a density of majority electrons, and then the spin diffusion length will decrease exponentially, as we discussed, with this parameter L and is d, which is spin diffusion length. So what you need to do afterwards, you need to integrate on this semi-infinite slab of the non-magnetic layer, like that. So from 0, which is our interface, to infinity, we are integrating, and we say that this is n0 LSD. It's equal to the total number of spin in the accumulation region. Yeah, so n0 we can name simply as spin accumulation. So the next question, what is the decay rate of the spin accumulation? And this one you can define as this total number of spin in accumulation region, and you just divide it with time of spin flip relaxation time, tau spin up down. I show it here, and what you do afterwards, you just plug in tau from this formula defined in terms of spin diffusion length, and when you put it here, you will get such a value. After simplest arithmetics, you will get such a value for the decay rate of spin accumulation. So this is term which describes spin relaxation, how fast we lose spin accumulation. But from another side, you have to put a source of spin, your spin injection, and this source of injected spins can be defined in simplest this formula, which is P, spin polarization, as we discussed, current density yet divided with E, and then just making this part spin injection equal to spin diffusion, as we discussed, they should be in equilibrium. You will get a value for the spin accumulation at the interface. So now you know that at the interface you have some value which is proportional to the spin diffusion length, because its two parameters should be in equilibrium. Therefore, spin diffusion length defines how many electrons you have at the interface. It's proportional to polarization. Also, if you would use non-magnetic material, for example, copper to gold bilayer, then polarization would be 0, and then there would be no spin accumulation. Again, you need to apply current, obviously, in order to get spin accumulation. And also, these parameters of material should be taken into account, Fermi velocity and mean free path of electrons. So this is nice formula which gives you the value for spin accumulation. So it tells you how many spin polarized electrons you have at the interface. And now let us estimate it. So we use simplest case of half metal, ideal spin polarizer P equal 1. Typical values for current, for example, 1000 amperes per centimeter square. Looks a bit too large, but don't be afraid, because usually in spintronics people deal with very small structures of cross-section 100 nanometers squared. Therefore, this value is not so horrible. And this is our Fermi velocity, and these are parameters which we already had. And we will get a value of 10 to the power of 22. So this is the density of spin polarized electrons per meter cubic. But if you compare it to the total density of electrons, it is 10 to the power of 28. So it means that spin accumulation is only a very, very small fraction of electrons of order of 10 to the power of -6. Yeah, so it's 10 to the power of 6 smaller the density than the normal density of electrons. So this is important message that we understand how strong is this effect. And at the same time, as I said, it's very pronounced. So all these spintronics phenomena, which I used already, the devices, they're based on all this. Yeah. Therefore, even such a small, relatively small effects, but if to use it properly, some case it defines, for example, resistance of your stack drastically. Yeah. So it's some key element. Therefore, the spintronics phenomena are very pronounced in spite of the fact that we have not so many, not so large spin accumulation, even in the ideal case. Few words at the end. This nice picture I got from the script of Gross Marx of spin electronics, and it's just a step back to summarize what we know already, and at the same time to attract your attention that in real structures there are more complex processes which should be taken into account if you want to understand what you see in your experiment, for example. And so here you see different types of metals. So for example, alkaline metal, which are very good metals, usually have one free electron per ion, and like natrium and so on. So then you have these metals like copper and silver, which are good conductors, and you see that they're good conductors because this d band is lying below the Fermi energy, so it means that you do not have additional scattering centers at the Fermi level. And then you have non-magnetic 3D metals like this one, vanadium, zirconium. Then you, in this case, you have d localized d band model at the Fermi level, and they are not very good conductors. And finally, we are coming to the magnetic 3D metals, where 3D band pieces located at Fermi level only for one spin polarization. So there's a spin down, and this is spin up, and then spin up electrons carrying from current better because they are not scattered on the d electrons. So usually we say the d electrons are localized, s electrons are not localized. But what we should take into account that first of all, if you have such a complex structure, you will modify s and d bands. So there will be hybridization of sd bands, and it means that this very simplest model not always applicable. Besides, you will get partial localization of s electrons, and they start filling ions, and there will be partial delocalization of d electrons, so they can also participate in the electric current. We should not forget about effective mass of s electrons. Yes, we said in one of the lectures that s electrons have higher effective mass than d electrons. Yeah, and finally, that's what we were talking already. It's a scattering of s electrons on the localized d electrons. So this is the message here, is just that keep in mind that all the models which we present in this basic course to give you just a general feeling, but if you want to try it deeper and deeper, you need to always to be ready that there are more complex physical phenomena which should be taken into account. Good, so we are done with spin injection and spin accumulation, and the next part is Hall effect. So there is nowadays people study a huge family of Hall effects, and this is a topic of the next lecture.